Good day. Today we're going to discuss the diagonal, triangular, and symmetric matrices. So in this discussion, we will have matrices that have various special forms. These matrices arise in a wide variety of applications and will also play an important role in the subsequent work. Okay, so diagonal matrices, a square matrix in which all the entries of the main diagonals are zero is called diagonal matrix. So as you can see in this example, okay, these are the examples of diagonal matrix. And as you can see, okay, outside the main diagonals are zeros. And if that would be the case, then uh, that would be a diagonal matrix. So in general n by n diagonal matrix, it can be written this one. Okay. So diagonal matrix is invertible if and only if all of its diagonal entries are non-zeros. In this case, the inverse of D, this one, matrix D is this one rather. And of course, powers of diagonal matrices are easy to compute. We are going to have this kind of, okay, what to call this one, expression. Okay, example, inverses and power diagonal matrices. So you have a matrix A, 1 0 0 0 negative 3 0 0 0 2. Okay, so in this case, we could have, of course, the inverse of A would be you have 1 0 0 0 negative 1/3 0, then 0 0 1/2. Okay, and of course the diagonal, the a a raised to 5 would be equal to 1 0 0 0. You have negative uh 243, then you have 0, then you have 0 0 32. Okay, so matrix products that involves diagonal factors are especially easy to compute, as you can see. Okay, in words, to multiply a matrix A on the left by a diagonal matrix D, we can multiply successive rows of A by the successive diagonal entries of D. And to multiply A on the right by D, one can multiply successive columns of A by the successive diagonal entries of D. Okay, so you have triangular matrices. A square matrix in which all the entries above the main diagonals are zeros is called lower triangular, and a square matrix in which all the entries below the main diagonal are zero is called upper triangular. The matrix that is either upper triangular or lower triangular is called triangular. So you have here the illustration. So as you can see, this one is upper triangular, and this is lower triangular. So observe that diagonal matrices are both upper triangular and lower triangular, since they have uh, zeros below and above the main diagonals. So also observe that a square matrix in row echelon form is upper triangular since it has zeros below the main triangular. Okay, so let's have properties of triangular matrices rather. Okay, so these are the four facts about triangular matrices that we will state without uh, formal proof. So you have here a square matrix A is equal to, of course, you have matrix A sub I sub j, A sub ij rather, is an upper triangular if and only if all entries to the left of the main diagonals are zeros. That is, the A sub ij is equal to 0 if I is greater than j. Then you have a square matrix A is equal to, of course, the matrix of A sub ij is lower triangular if and only if all entries to the right of the main diagonal are 0. That is, the A sub ij is equal to 0 if I is less than j. A square matrix A is the matrix A sub ij is upper triangular if and only if the ith row starts with at least I minus 1 zeros for every I. E square matrix A is equal to the matrix of A sub ij is a lower triangular if and only if the jth column starts with at least j minus 1 zeros for every j. Okay, so you have the illustration on the right side. So this would be the theorems, okay, for the basic properties of triangular matrices. So you have a transpose of a lower triangular matrix is upper triangular, and the transpose of the upper triangular matrix is a lower triangular. The product of lower triangular matrices is lower triangular, and the product of the upper triangular matrices is upper triangular. A triangular matrix is invertible if and only if its diagonal entries are all non-zero, and then you have the inverse of all invertible lower triangular matrix is lower triangular, and the inverse of the invertible upper triangular matrix is upper triangular. So in the first, okay, part of the theorem, it is evident from the fact that transposing a square matrix can be accomplished by reflecting the entries from the main diagonals, and then you you, you you have that kind of scenario. Okay, so let's have this one example computing with triangular matrices. So you have to consider the matrix A and matrix B. Okay, so in this case, uh, take note that on the part C, triangular matrix is invertible if and only if its diagonal entries are all non-zeros. Okay, so in this case, we have uh, the matrix A is invertible. Okay, it's clearly to see, no, that matrix A is invertible and matrix B is not. Moreover, the theorem also tells us that the inverse of matrix A, the AB and BA, must be the upper triangular. Okay, so I want you to uh, do the manual computation and verify that in this case, A is equal to, the inverse of A is equal to 1 negative 3 halves, then 7 fifth, then 0 1 half, then negative 2 fifth, and then 0 0 1 fifth. Then AB would be 3 negative 2 negative 2, you have 0 0 2, then 0 0 5. Then BA is equal to 3 5 negative 1 0 0 negative 5, and 0 0 5. Okay, I want you to do the manual computation, okay, to verify this answer. Okay, so let's symmetric matrices. Definition 1: a square matrix A is said to be symmetric if A is equal to the transpose of A. So it is easy to recognize a symmetric matrix by, of course, inspection. So the entries on the main diagonal have no restrictions, but mirror images of entries across the main diagonal must be equal. So like this one, this illustration. So you have the main diagonal, and then as you can see, other than the main diagonal, they are equal. So all diagonal matrices, such as on the third matrix, okay, is actually uh, it has the same. Okay, so like this one, this is symmetric matrices. Okay, so let's have theorem 1.7.2. Okay, so this would be uh, the properties of the algebraic properties of symmetric matrices. So you have, if A and B are symmetric matrices with the same size, and if K is as any scalar, then the transpose of A is symmetric. A plus B and A minus B are symmetric, and KA is symmetric. Okay. So theorem 1.7.3. The product of two symmetric matrices is symmetric if and only if the matrices commute. Okay. So here we have an example. Okay. Uh, as you can see, the first of the following equations shows a product of symmetric matrices that is not symmetric. And the second shows a product of symmetric matrices that is symmetric. So we conclude that the factors on the first equation do not commute, but those in the second equation do. Okay. So we have invertibility of symmetric matrices. Okay, so in general, a symmetric matrix need not to be invertible. For example, a diagonal matrix with a 0 on the main diagonal is uh, symmetric but not invertible. However, we have the theorem shows that if uh, a symmetric matrix happens to be invertible, then its inverse must also be symmetric. So, which is the theorem 1.7.4. If if A is an invertible symmetric matrix, then the inverse of A is symmetric. Okay, so products of A and transpose of A and the transpose of A times A. So mm, matrix products of the form uh, this one, A times its inverse, its transpose rather, and the transpose and A arise in a variety applications. If matrix A is um, M by N matrix, then the transpose is N by M matrix. So the products of A and the transpose of A and the product of transpose of A times A are both square matrices. Okay, so the matrix A times A raised to T, or the transpose of A, has the size of M by M. And the matrix uh, transpose of A times A has the size of N by N. So such products are always symmetric. Okay, since you have you have A times A raised to T times T is equal to uh, A, the transpose of A times the transpose, then you have A transpose, which is equal to, this one is actually A, then this is A transpose, and you have the transpose of A times A. If we are going to transpose that one, you have transpose of A times transpose of A and its transpose, which is equal to transpose of A times A. Okay, so you have here example, the product of matrix and its transpose is symmetric. So let A be the 2 by 3 matrix. So that one. So uh, the what do you call this one? The transpose of A. Okay. So I want you if we are going to get the transpose of A here, the transpose of A is equal to, you have uh 1, -2, 4, 3, 0, -5. Okay. So if you are going to have transpose of A times A, so you have here, this is 10, -2, -11. That is 2, -2 rather. I'm sorry. 4, -8. Then you have -11, -8, then 41. Okay. And then if you have A times the transpose of A, you have uh, this is 21, -17, -17, and you have 34. Okay, so observe that a transpose of A times A and A times transpose of A are symmetric as expected. So later in this discussion, we will obtain general conditions on A under which the product A and transpose of A and transpose of A times A is invertible. However, in the special case where A is a square, uh, we have the following results. Okay, so theorem 1.7.5. If A is invertible matrix, then you have A times transpose of A and the transpose of A times A are also invertible. Okay. So, of course, since A is invertible, uh, transpose of the transpose of A by theorem 1.4.9, okay, is also what to call this one? Since A is invertible, so the transpose of A is also invertible according to theorem 1.4.9. Therefore, the product A and transpose of A and the transpose of A times A are invertible since they are the products for invertible matrices. And that's all for this presentation.